the month. This year is the 50th anniversary of the first commercial monolithic IC. Now there are hybrid integrated circuits, there are monolithic integrated circuits. The monolithic integrated circuit really is the important one. That's the one in silicon that has made a tremendous difference in the world. March 1961, Fairchild introduced a 5-transistor integrated circuit, a flip-flop. Not too exciting by today's standards, but it did cost several $100s, and it was the start in their micrologic family. Now, of course, the integrated circuit has great importance. This statement by Gordon Moore, who's one of the founders of Fairchild and one of the founders of Intel, really, I think, is very significant. And it says, and you are once again reminded that this is no longer just an industry, that is the semiconductor industry, or the integrated circuit industry, but an economic and cultural phenomenon, a crucial force at the heart of the modern world. How many things does the integrated circuit touch? Certainly all of communications. Almost everything we have now either has an integrated circuit in it, or will have probably someday. Appliances at home, obviously televisions, cell phones, et cetera, et cetera. So it's immensely important. So let's see, Ollie, I think.
Does it go?
Okay, let me get rid of that. Okay, so just in case you'd like to dig a little deeper into this, the first 5 books are really very important books in this particular area of the integrated circuit. If you're interested in Robert Noyce, and he's a very interesting person, Leslie Berlin's book, published back in 2005, is really a very interesting biography of Robert Noyce. I highly recommend that because he was a real interesting entrepreneur. When he was a kid, the one story I really remember is his friends, they built a sort of a large replica, I think it was about a 20-foot wingspan replica of the Wright brothers biplane. And in order to try it out, Robert Noyce climbed up on top of the largest barn. He grew up in Iowa. The highest barn they could find, strapped the wings around him and jumped off the barn, and it flew just well enough so that he wasn't injured. But it wasn't great. But anyway, that was Robert Noyce. Always at the cutting edge, pushing things a little bit. So.
Somehow it happens that
okay.
It seems that.
So anyway, these books are highly recommended. This book by Saxena is fairly recent, and it goes into a very deep discussion of the patents that are involved with the integrated circuit. Okay, so now I think we're on the air. Okay. All right, so now I want to give tribute to a couple other places where you can find out a lot about this. Computer History Museum in Mountain View, it's on 101. I highly recommend it. It just opened in January with 19 major new displays. This issue of Bloomberg Business Week magazine, last week's issue, has a major article on this particular museum. It's very seldom that Business Week would ever do something like this, but this they recommend it highly. It's really worth visiting. And it captures a great deal of the history of the computer, all the way back to the very early vacuum tube computers. It has material on how Apple evolved in Silicon Valley and so forth. The other thing I'll cite is that Stanford has 2 projects. There are Silicon Valley Archives and the Silicon Genesis. And for about 20 years, they've been collecting a lot of information in terms of interviews and panel discussions and that type of thing. A real resource for anybody interested in Silicon Valley. Okay, so now to the invention. The short version. Well, if you only just want to know the short version, it's really very simple. There are 2 men, Robert Noyce and Jack Kilby. The integrated circuit was invented in 1959. Well, Kilby actually worked on it in 1958, but that's a detail. Kilby was at Texas Instruments. Well, that was an interesting little company out in Dallas, Texas, all by itself out there. Robert Noyce was at Fairchild Semiconductor. He was one of the 8 traitorous founders that left William Shockley's Shockley Semiconductor. And the IC patents were granted during 1961 and 64. Kilby filed first. Noyce received the first patent on it. TI was not happy. A patent war began. We'll talk about that a little later. Anyway, that's the short version. Very, very simple. And in 1999, the United States Postal Service recognized the major importance of the integrated circuit and issued this stamp. You see both the front and the back of the stamp. Now, most stamps don't have a small amount of text on the back of them, or the glue over it. But this is an early integrated circuit. It looks like a Fairchild layout to me. By the way, postage was, in 1999 was 33 cents. But anyway, and their version was independently invented by Kilby and Noyce. The integrated circuit was first available commercially in 1961, as we know. And it led to smaller, inexpensive mass-produced electronic circuits, revolutionizing the computer industry. Well, good for the post office. I don't think they issued a 50th anniversary stamp, but okay, we'll give them credit for that. Now, in the course of this talk, I want you to focus on 3 things. Keep these 3 things in mind. Integrated circuit. Well, we have to have integration. That means we can't just take a single transistor. We have to have multiple transistors and other components like resistors, capacitors, etc., and put them together on a single crystal chip. Well, if you have multiple multiple transistors, you have to isolate them. They can't talk to each other except the way you intend for them to be wired to talk to each other. So if it's a single piece of silicon, you don't want them to communicate through the substrate itself. So you have to have a method of isolation. And third, and this turns out to be really important, and you'd think it'd be very obvious, interconnection. You have to connect these devices together in a coherent way to perform a function. That turns out to be very important. Okay, so let's start with a little bit of history. Let's go back to the ENIAC computer, which was a masterpiece of a computer when you think about what this actually accomplished at the University of Pennsylvania. But let me point out a couple things. Yeah, people like to talk about what it could do, like 5,000 numbers per second could be added. And it was 1,000 times faster than a mechanical calculator. That's a real step forward, isn't it? That's great. And it had vacuum tubes. There were almost 18,000 vacuum tubes. That's why it consumed so much power. Just think of your laptop consuming it. It would melt.
By the way, Don,
Yeah.
when I say Semiconductor, that's the university I graduated from, and still that computer was down in the basement. And one of my professors, who was a graduate student in those days, he told us that it took them many years to work together with other professors. I mean, he was a student, was in some graduate, just to go and solder this big thing.
Yeah.
Look at that. I mean, these 17,000 vacuum tubes, each of them have like maybe 5 to 6 to 7 or 8 type of connections.
Now, that's a great lead into my next point.
Yeah.
5 million hand-soldered joints.
Thank you. Yeah.
There were 2 problems with this, because think about it, this is one of the very, very earliest computers. You're going to want to improve it. You're going to want to go faster. You want to increase the computational capability. Well, the vacuum tubes, they burn out. They don't have a very long life when you start talking about huge numbers of vacuum tubes. So we have the vacuum tube problem. The other one is the tyranny of numbers. Suppose you were to build a computer with 10 times this capability with 50 million hand-soldered joints. Who's going to do all the soldering? Big problem. This tyranny of numbers was a big deal, a very big deal. And a lot of people were aware of it. In fact, Jack Morton at Bell Laboratories wrote a book that talked, part of the book talked about the tyranny of numbers, and sometimes called the connection problem or the numbers barrier. Basically, it was that it was going to be really difficult to advance the state of the art in computers if you had to deal with this huge numbers of interconnections. I mean, you might even make a mistake in wiring all of these when you talk about many, many tens of millions of interconnects. So it was wiring limited, and both, very important, both Robert Noyce and Jack Kilby were very aware of this tyranny of numbers. Now, William Shockley used to give talks where he would talk about the dynamics of invention. And one of the things that he would often cite is the will to think. And he claimed that most major inventions, you have to have some will to think. There has to be some motivating factor. In fact, he attributed this idea to Enrico Fermi, the famous physicist from Italy. So this, I think, constitutes at least part of the will to think for both Noyce and Kilby for the integrated circuit. Now, the transistor came along in 1947, so this dealt with the vacuum tube problem. And in fact, this shows the first transistor that actually John Bardeen and Walter Bratton did. Shockley actually didn't have a lot to do with it. Shockley, immediately after the invention, was demonstrated with the point contact transistor. And the point contact transistor, incidentally, never really was truly significant in terms of making a large impact. The bipolar junction transistor turned out to be the embodiment of the transistor that was very important in the first 10 to 15 years. Then the MOS transistor started to dominate. Incidentally, Western Electric made point contact transistors for about 10 years before it was discontinued. So people did use them. Anyway, the vacuum tube problem was solved, and the transistor was coming along, and so people were very interested in how do you make these. And that's what we're really going to be concerned with in the integrated circuit. That plays a very important role. Now, I said there were three factors. One of them is integration. Noyce and Kilby didn't come up with the idea of integration. The first reference that I've been able to find to integration, once the transistor had been invented in December of 1947, was Jack Morton himself in a memo. Geoffrey Drummer published a very famous paper at a conference where he talked about it. Harwick Johnson, I'm going to show you a patent where he talks about integration. This one is very interesting because Richard Stewart worked at TI along with Jack Kilby. I've never been able to understand the Kilby-Stewart relationship. And there were others. Barney Oliver at HP, who originally was at AT&T Bell Labs, but he joined HP about this time, and he published something on the integration. So the idea of integration was pretty obvious, I believe. There were a lot of people that were coming up with the idea. These are just some of the first official sightings of it. I'm sure there were a lot of people that talked about it that never really published. So integration itself was not a really new idea at the time of 1959 when the patents on the integrated circuit were actually published. Here's that memo from Jack Morton in '49, and I quote, "Imagine a technique in which not only the connecting leads and passive elements are printed, but also the active semiconductor elements are printed in one continuous fabrication process." A little different wording, but that's the idea of integration. Geoffrey Drummer in 1952, when he made his presentation, commented, with the advent of the transistor and the work in semiconductors, it seems now possible to envision electronic equipment in a solid block. In other words, a single piece of semiconductor with no connecting wires, meaning the wires were printed at the time of fabrication. In 1956, Drummer actually was able to receive some funding, but he really had no real chance of making an integrated circuit because his funding was way too small in order to actually fabricate semiconductors to the degree that it would have taken for integration. But he was clearly an early advocate of this. This is a patent that I think is really interesting. It was filed in '53, and what you see is this clearly is a piece of semiconductor, an N-type and P-type region. This is the NPN transistor itself, emitter, collector, and base. And it's a phase shift oscillator where it's a collection of CR circuits. So that the total phase shift of these three segments are 180 degrees plus the inversion of the transistor gives the 360 degree inversion for the oscillator. These devices are the capacitors, and the bulk semiconductor is the resistance. And in fact, Harwick Johnson went so far as to say that we could make a PN junction for these capacitors and have a distributed resistance for this RC feedback loop. Now, I think this is interesting because, first of all, Johnson never built it, but he patented it. And you will see this phase shift oscillator again with Jack Kilby, which tells me that I believe Kilby actually was aware of this patent when he filed later in '59. Richard Stewart, I just throw this in for completeness, but I have no idea how much he had talked with Kilby. He filed 6 days after Kilby filed his patent on an integrated circuit. So they must have talked. And it's clear that he talks about the interconnect problem. And he actually appears with his drawing to have done something with the interconnect problem. But it isn't completely clear how he did it. So this patent turns out not to be too significant. But I note it because it does exist, and it was filed, and it was actually granted. Okay. Now we're going to go forward and just talk about what was the situation for semiconductor companies in 1959 when Kilby and Noyce filed for the integrated circuit patent. The East Coast had almost all the semiconductor companies. They dominated. Well, names like RCA, Philco, General Electric, et cetera, et cetera. So, and Western Electric, how could we forget them? AT&T, Bell Labs invented the transistor. They were very heavily involved in this. There were a few companies on the West Coast. Very few. They weren't very significant companies. Hughes Aircraft primarily initially started with diodes. Pacific Semiconductor was TRW. They were interested in government contract work. And there was this new company called Fairchild Semiconductor that was started in 1957. Turns out that William Shockley, in fact, well, actually, I'm getting ahead of myself. I think I've got a couple slides on that. Let me talk a little bit first about Jack Kilby. Kilby is a very interesting individual. He was a real inventor. Let me give you an example. Around 1950, Jack Kilby saw an advertisement for a company that brought out a micro sand blaster, in other words, very fine sand, that they intended for dentists to use to drill teeth. Now that was a real failure because nobody wanted to have their mouth filled with sand while their tooth was being drilled by a dentist. Kilby remembered that for some reason. So when Kilby worked at Central Lab, which was a part of this Globe Union Incorporated, he was working on thin film circuits. And one of the problems was how do you trim the resistors? In other words, how do you deposit the resistors, but they may not be the value you want, so you have to trim them. And he remembered this little micro sandblaster for dentists. So he got one, and he found that was a really great way to trim resistors on thin film circuits. And people to this day use sandblasting to actually trim those circuits. That's the kind of person Jack Kilby was. He was a real inventor. He actually did a lot. He was involved in inventing the first transistor radio, for example, at TI. But in June of 1958, Jack got restless and he joined this new company, Texas Instruments, that had gotten into semiconductors. Dallas, Texas, the only company in Dallas that was involved in semiconductors. Previously, they had been involved in the oil industry. So And incidentally, there is no U.S. stamp that I could find that honors Kilby, but the Marshall Islands did. So, and that's maybe not the best picture of Jack, but that's what they offered with their stamp. So, just to kind of give you an idea of what happened, so Jack joined TI, and it turned out most of the people around him in the research lab were on holiday. So he was pretty much alone in the lab, and he started thinking about this tyranny of numbers. And he came up with the monolithic idea. So in July is the first reference, July 1958, first reference when Jack listed the idea of a simple flip-flop made with a single piece of semiconductor. Okay, in August, he demonstrated this by putting discrete components together, and he demonstrated that the circuit would work. September, this is all happening really fast now. He demonstrated this phase shift oscillator. And the drawing of the phase shift oscillator will appear in the patent that's eventually filed. Then he demonstrated also in September this flip-flop. He designed an all germanium, not silicon. TI was still working very much with germanium. They were also starting to work with silicon. They were one of the leaders in silicon. In an early, probably around January of 1959, Kilby actually demonstrated working flip-flops. Now, it turns out that in February, this is an important date, February 6th, Jack Kilby filed. And I'm going to say a little bit about why in a moment. TI, you'll note, announced solid circuit invention. But this was really, this solid circuit inside that package where the lid hides what's in there, those are discrete elements that were just wired together. It was a hybrid integrated circuit. It was not a monolithic integrated circuit. But TI started to sell these, and by the way, they were a little bit expensive. A little bit expensive. And I'll talk about that in a little while. Okay, so here's the phase shift oscillator that Jack built. Indeed, single piece of germanium, okay? But look, he's using wire bonds. So remember I said we have this interconnection problem that we have to deal with? Wire bonds, think of an Intel microprocessor with all wire bonds on the chip. Couldn't do it. Absolutely impossible. So this is more like a hybrid, even though there's some integration between the capacitance and the resistor being the bulk of the semiconductor itself. So it was filed in February 1959. It was issued 5 years later. Keep that in mind. That will be interesting. Here's the flip-flop that Jack Kilby worked on. Look, he actually had etched a slot in the piece of semiconductor. This again was germanium. These are Mesa transistors. This slot is in there, so you have a resistance. This is a contact. So here are the resistors formed by this part. So it truly is integrated. He has combined these in such a way it is integrated, but it's all wire bonds. This is called the flying wire picture. That turns out to be very important. And you will find in the history of patents, little details turn out to be really important. So I'll make the comment, this is more like a hybrid integrated circuit than really a true monolithic integrated circuit. Okay, so what happened then? Well, in January of 1959, somebody at TI had gone to a conference and brought back a nasty rumor. And the rumor was somebody, didn't know who, was working on an integrated circuit or had come up with an integrated circuit. What happened? Panic. At this point, Kilby had not worked out the interconnect problem. They thought about it a little bit, but they were still using the wire bonds. So they went to the master of patents, the attorney of attorneys for patents, Mo Mosher, who was stationed in Washington, D.C., and he said, we got to file right away. So he sent an assistant to Dallas, They worked for a week and came up with a patent disclosure. Panic had accelerated the filing of this. And here's a sentence in that patent application that turns out to be truly crucial. Instead of using gold wire in making the interconnects, connections may be provided onto the semiconductor circuit wafer. The wafer means it's a single piece of semiconductor material. A material such as gold, that turns out to be important, may then be laid down on the insulating material to make necessary electrical interconnects. Now they thought they had covered all their bases. No matter what people will come up with, either print wiring on it, or do some type of patterning or etching or whatever, they thought they had covered their bases. They said, no. Okay. And they waited. Okay. Meantime, far away in another technology galaxy, a galaxy that was to become very prominent, Silicon Valley, of course, just a few miles from us, things were happening. Let's talk about that. In 1955, William Shockley, who received the Nobel Prize along with Bratton and Bardeen for the invention of the transistor, Shockley's real contribution was the theory of the bipolar junction transistor. Extremely important contribution. He decided he was going to get rich. He was going to come to Silicon Valley. Well, it hadn't been called Silicon Valley yet. He didn't know that. In fact, I remember Jim Gibbons at Stanford once made the comment, he said it was really fortunate for us that William Shockley's mother lived in Palo Alto and not in Berkeley. Well, anyway, Shockley got backing, and on San Antonio Road, if you happen to be familiar with the area down in the Mountain View area, actually the first time I saw that building was a flower shop. Things changed rapidly in Silicon Valley. But anyway, Shockley set up this laboratory. Now keep in mind at this time, you couldn't go out and buy semiconductor manufacturing equipment. Nobody sold any of that. So Shockley was really good at one thing. He could recruit really good talent. He had a real touch at doing that. And he went out and recruited a lot of people, some very, very good people. People like Robert Noyce, Gordon Moore, Jean Hernay, Jay Last, Gene Kleiner, and so forth, and a number of other people that aren't quite as famous. And they started Shockley Semiconductor. Well, things went along for about a year. Shockley was a really hard person to work for. This is a story unto itself. But there was a revolt. 8 of the key people decided, we're not taking this anymore, we're leaving. Some very interesting names. Robert Noyce. Well, Gordon Moore doesn't play the major role in the invention of the integrated circuit. He was an observer of it, but Noyce and Moore eventually founded Intel. Jean Hernay, and really one of the reasons I'm giving this talk is I want to talk about the contributions of Jean Hernay and Jay Last, these 2 individuals. Noyce and Kilby get all the credit in the short version of the story, but Hernay's contribution and Jay Last actually was the person that built the monolithic integrated circuit. These people also deserve a great deal of credit. So, now, the planar process is the key to the monolithic integrated circuit. Here are 5 things that you absolutely have to build a planar, modern integrated circuit. You have to have a very good material. Well, germanium wasn't really it. Germanium has a very high hole mobility, which is really good, but a lot of things it doesn't have, like it doesn't have a good native oxide. It has a very narrow band gap relative to silicon, and it doesn't do well at elevated temperatures. So that's a real negative on it. Silicon turns out to be really great. And Gordon Teal from Bell Labs was hired by Texas Instruments to really start silicon work. TI wanted to use silicon. They were one of the real proponents of that. Bell Labs also realized that silicon was very important. You also have to have an extremely high quality insulation layer to put on the top of this semiconductor. Silicon turns out to just have the greatest layer possible. Silicon dioxide, silica, sand, whatever you want to call it. It's really good and it's easy to grow. You have to be able to form ohmic contacts to contact the various regions of the transistor. You have to have interconnect, and it turns out on silicon dioxide and silicon, aluminum is the godsend material. They really got lucky, because aluminum forms a really good ohmic contact very easily, and it also sticks really well to silicon dioxide. And then finally, you have to be able to pattern the insulation layer, so you have to have some type of patterning technology or photo engraving. And it turns out that putting a layer of a photoresist and exposing that and etching various regions selectively in the oxide is really what's needed there. So let's talk a little bit about the work that people did laying the stage for Noyce and Kilby. Because if this work hadn't been done, I doubt Noyce and Kilby would have been able to reach where they ultimately ended up. So incidentally, if you go back to about 1952, only about 10,000 discrete transistors, individual transistors, were built that year. That was kind of the state of the art at that time. I cite Shockley's work. I don't know how many of you may have read even part of Bill Shockley's Electrons and Holes and Semiconductors, but that is still one of the best books ever written explaining the behavior of semiconductors. I highly recommend it. So we have to introduce doped regions into a semiconductor to make transistors. You have an NPN, you have to have an N layer, a P layer, and N. So the early work started at Bell Labs to form PN junctions by using thermal diffusion. You introduce impurities into the semiconductor material, and by elevating the temperature, you can drive those impurities in. And that work was really done at Bell Labs, and in fact, TI also was able to do a ground junction transistor, where they also used diffusion. And but this early work was extremely important. Now, at that time, the very early work, they just diffused layers into the entire wafer of the silicon. They didn't pattern it. They could diffuse both sides of the wafer if they wanted to. Okay, then there's oxidation. You need this oxide layer, and RCA actually did some very important work on this. But again, Bell Labs turns out to have done the really important work on this. And the work of Frosch and Derrick at Bell Labs in growing silicon dioxide is really the premier work that was very instrumental here. This is from a paper by Frosch and Derrick, and you can see in quoting from that paper, they noted that the use of oxidizing atmospheres has been shown to provide surface protection. That was very important. Protection. That silicon dioxide layer was protected, and it also could be used as a mask to diffuse impurities. So it did double duty. Very, very important. This shows an angle lap of a wafer using staining and clearly indicating they have an NPN structure by using oxide masking with diffusion, with a diffusion technology. So at the University of Illinois, Nick Polanak, who is very well known in the semiconductor field, he wrote a review paper a few years ago, and he basically said that Frosch and Derrick had laid the groundwork for a revolution. He basically noted that they really understood the importance of the oxide layer, and they developed the technology for growing steam-grown oxides. You can also do it with dry oxygen. Steam growth was faster. You could grow thicker oxides quicker. Okay, theme, Bell Labs. We'll mention that again at the end of this talk. And they showed in their patent that they could etch the oxide with the appropriate etchants. Today, most of the processing in silicon technology is dry etch or plasma etches, but this was all wet chemistry etching. And indeed, they showed that you could pattern the oxide and then use those openings to diffuse selective areas in the semiconductor itself. Here is a paper, actually it was a patent by Lathrop and Noll, showing that you could use holes in silicon dioxide to fabricate diode arrays. What I think is really interesting is Noll, not too long after this patent, went to Fairchild, and Lathrop went to TI. That must be a coincidence. Strange coincidence. Here's, in my opinion, the real hero, Jean Herné. Jean Herné was one of the people hired by Shockley. Incidentally, Herné shows that you may need 2 PhDs in physics, but I doubt that's really true. Where Shockley found him is he was a research fellow working in Linus Pauling's lab at Caltech, and recognized he was a very bright guy, and he hired him for the Shockley Semiconductor operation, along with all these other people. And he was one of the founders. He was one of the traitorous 8 that left Shockley. Shockley was really stunned when this happened. And he was a founder of Fairchild Semiconductor. Herné was a hard guy to work with, I'm told. I've heard this from many, many people. He soon moved on to found a company at Teledyne, and then another company at Union Carbide, and so forth. He was never really satisfied being one place very long. Very bright guy, though. And the reason this is important, Herné's work, is the following. Now, here's the background. Up to 1958 and into 1959, the majority of transistors being built were diffused Mesa, which meant you took a piece of silicon, you diffused in a P region everywhere on the wafer. Then you diffused an N layer everywhere on the wafer. And then you would, across the wafer, you would form contacts. They could be alloy contacts. There are several ways of forming contacts. I don't want to worry about how to actually do that. And then what you would do is you would etch the material away to isolate these devices. And you'd have a lot of devices on a wafer, and then you'd cut off the wafer, and you'd have all these discrete transistors that you could then package in a header, something like this. This is a Fairchild advertisement from, I believe, about 1958. See this surface at the edges of the junction? That was a big problem for reliability. You had a lot of leakage, you got moisture into the package, you could get degradation at those junctions, you could get leakage across the junctions. If you had something rattling around, like a little metallic particle inside, you could get shorting. The military was really unhappy with these. They liked the transistors, but they didn't like the reliability. So here's the will to think for Jean Herné. How do you make this a reliable transistor? So Herné, who had just joined Fairchild, started thinking about this. How do we make this reliable? And in December of 1957, 2 years, about a year and a half before the patents for the integrated circuit, he came up with the idea that the oxide layer so obtained is an integral part of the device and will protect the otherwise exposed junctions from contamination and possible electrical leakage and subsequent handling, cleaning, and canning of the device. Key idea, really key idea. And he will eventually get around to filing for a patent on this. Now, he'd been working on PNP transistors at Fairchild because Fairchild was a startup. They didn't have any sales. You can't last very long as a startup if you don't have income coming in. So Herné was really working very hard to get product out. But he found time in May of 1959 to file a patent, and this is the planar process patent that was filed in, or rather granted in March of 1962. This is a really key patent. There are some people, and I'm one of them, that believe that Hernay probably should have been included on the integrated circuit. Because this was the key. This was the key to the monolithic IC. Robert Noyce is going to come along. He is well aware of this because he works with Hernay, and Robert Noyce is going to come along and use this. Now, the planar process itself, you see, gets rid of that etching of the Mesa. So you take the semiconductor, take N-type, grow an oxide, open a window using photo engraving or photolithography, diffuse in the P-type base, and while you're diffusing this in, grow an oxide simultaneously with it. And then you open up this oxide with a smaller cut, and you form the emitter base collector. So the collector's on the back, and then you open up regions so that you can make contacts. The first geometry that Fairchild made with this planar process was the ring dot geometry, the old 2N1613, and that was actually designed by Gordon Moore in 1959. And Gordon Moore did get into the act. He designed the transistor. He did a lot of things, so he just was not the main person here. Now, it turned out that Jay Last was the person that his group really fabricated these devices. So Jay Last is the person, in my opinion, that demonstrated the application. He's the one that demonstrated or showed it really worked. He made the first working units. And in March of 1960, Fairchild announced in New York at the IRE, that's before it became IEEE, and they talked about the planar structure. This is Jay Last. This is Tom Bray. Tom Bray, I believe, was in sales and/or marketing. That's from the Electronic Daily newspaper, which was a common way to communicate in those days in the electronics arena. And if you can't really tell from that picture, but if you look at that picture carefully, it isn't accurate. Fairchild didn't want to give away their secret. Well, we've never heard of that before. One final thing. We've got to talk about isolation. And the forgotten guy, the guy that really doesn't get a whole lot of credit here, but actually patented the use of PN junctions to isolate arrays of transistors, was Kurt Lithography. And Noyce later, in a Scientific American article on microelectronics, actually acknowledged Lithography's role. But he often is never even mentioned in the integrated circuit invention. But that is a key part of the integrated circuit, the monolithic silicon bipolar integrated circuit. You have PN junction isolation. Okay, so along comes Robert Noyce. And Robert Noyce, a very brilliant guy. He's really good at integrating things in terms of bringing people together and getting ideas. Noyce didn't probably do a lot of the hands-on work himself, but he was good, really good at getting people to cooperate and contribute, and he was a natural leader in many, many ways. In fact, he was the chosen leader among the 8 that left Shockley. So, very interesting individual. And he was a part of the starting of Fairchild Semiconductor. And Robert Noyce and Gordon Moore are often focused on very, very heavily at Fairchild. Then they left later in 1968 to start Intel. And of course, that's another story into itself, what happened at Intel. That would make a very interesting talk. Okay, this is actually the first integrated circuit that Jay Last fabricated. They actually made more than just this one. And you might ask, well, why is it round? Isn't that kind of strange? Aren't they usually rectangular? Well, they wanted to put it in this package, this 6-week package. So they deliberately etched it in a round geometry so it would fit into that package, and then they could wire bond from these pads to the tops of the posts in that package. That's why that chip is round. This is the patent that Noyce filed. Now remember, in February 6th, Kilby filed. This is now July 30th. Just before this, Jean René filed his planar patent. But here, I show this figure because the circuit itself isn't all that interesting. But what you see is the p-n junction isolation. Indeed, there are multiple components of resistors, diodes, and a transistor in this structure. This is the diode, this is the transistor. And you can see there is interconnect metal, a pattern of interconnect metal on the surface. All the ingredients, integration, isolation, interconnect, all three of those ingredients are all in that pattern. And it was filed. Now I want to talk a little bit about timing. Okay, so here we have September, Fairchild is launched. December, René conceives planar process in 1957. Okay, in the meantime, Fairchild is introducing product, but it's a Mesa transistor. Core driver means it drives magnetic cores, ferrite beads. Okay, January of 1959. Remember, Kilby, during the latter part, last half of 1958, had been working on his integrated circuit idea. Noyce says, this all makes sense, and he writes this down in his notebook. February 6th, TI files patent. March 59, TI announces solid circuit. Now remember, it's a hybrid, it's not a monolithic. Okay, the first planar transistor was produced at Fairchild in March of 1959. And René files his patent. Then Noyce files his patent application. In May of 1960, about a year later, the first fully working IC made by J. Last is actually demonstrated. My personal feeling is you can write down all the ideas, but reduction to practice is very important in the invention process. Okay. And then some other things happen. So what happened now is, even though Kilby filed first, it turns out that Noyce receives the patent first. Well, TI wasn't really happy with this. Okay. And it's going to turn out that this interconnect will prove to be extremely important. For some reason, Noyce's patent really just flew through. It took about 2.5 years versus 5 years for Kilby. And this is going to turn out to be a really huge issue because Noyce had all three ingredients and it showed that, indeed, in fact, they used aluminum to actually form the interconnect on those integrated circuits. And I think it might have been Gordon Moore that suggested aluminum, using aluminum. That's another point where Gordon Moore comes into this, if I recall correctly. I'll have to double check that. So anyway, what happens is, here's the sequence of events. We have the patents filed, Kilby first, and the patent office, actually even faster than I thought, issues the patent to Noyce. Oh, TI was unhappy about that. What do they mean he gets it first? So they immediately challenge this. And the patent office reviews this for, it looks like, for about 3 years. You know, justice doesn't really move fast in this country. And they say, oh, Kilby clearly has the right to the patent. Well, now Fairchild wasn't happy with that, so they immediately challenge it. Okay. But in the meantime, you have to do business. And it's very much to the credit of TI and Fairchild that they worked out a deal and said, we will share royalties. It's okay, we can share royalties. They had already worked it out. So the interference board rules that the TI patent rules, Fairchild, as I said, appeals it. Okay, the Court of Customs and Patent Appeals is late now. We're not 1969. We're 10 years later. They say, oh, wait, there was a mistake. Fairchild really is the right patent. You have the rightful claim to the integrated circuit. TI doesn't like that. They appeal to the Supreme Court. The Supreme Court says, we're not getting involved in this. Done. Robert Noyce is officially the IC inventor. That's actually what happened. It took over 10 years in this patent litigation to resolve that. Fortunately, back in 1966, TI and Fairchild had worked this out. So it's a long sequence, but here's the bottom line. Essentially, I think almost everybody acknowledges that Noyce and Kilby were major contributors here. They both received the National Medal of Science and are listed as co-inventors. Kilby's credited with building the first working circuit with all components using semiconductor material, and Noyce is credited with the metal over oxide interconnection scheme that gives us the full monolithic approach. In 2000, Jack Kilby received the Nobel Prize. Robert Noyce did not, because he had died before that. You cannot receive the Nobel Prize unless you're alive. I'm sure that Robert Noyce would have received the Nobel Prize along with Kilby had he been alive at that time. Okay, now here's something, I'm just about done. Here's something I think you will find very interesting. In the 2000 Nobel lecture that Jack Kilby delivered, here's what he said. He said, today it is a little hard to believe, but in 1959 as we began to announce this idea, and Fairchild discussed Noyce's innovations, there was tremendous criticism. Everyone here knows that the integrated circuit is a great invention. You couldn't do without it. Who could ever question that? But at the time, it was not obvious that this was even going to succeed. I find that amazing. Why? Why was that true? Well, when you see the reasons, you'll probably say, well, yeah, I can understand that. In 1959, when people were making these discrete bipolar transistors, the yields were about 10%. Now, you would do a quick calculation and say, let's make an integrated circuit with 10% times 10%, 1% yield. Well, it turns out that the planar process actually improved yields, and these discretes had to go through a lot of different parameters and hurdles. But in the integrated circuit, they only had to work together. You didn't have all these hurdles of the various parameters. A lot of the parameters, if you go back and look at the parameters on data sheets in the 1950s, you'll find there were a lot of parameters that nobody ever used. But they were just thought, you ought to have them because maybe somebody will need them. It was more important you had matched components than the absolute values for, say, beta and breakdown and that type of thing. Oh, but you can find much better materials for resistors and capacitors. Semiconductors like silicon don't make very good resistors, the high TC, temperature coefficients. Can't make very good capacitors or very high value capacitors with those. But designers are very clever. They can work around these things. They find ways to get around it. This is the more interesting one. It threatens circuit designers doing discrete component circuit design. It'll put them out of work. There was a lot of fear. Of course, it turned out that there were a need for more monolithic integrated circuit designers. And by the way, the integrated circuit didn't immediately put discrete design out of business by any means. Okay. In my opinion, this is really truly crucial for the early integrated circuits. They were very expensive. You could build discrete designs much cheaper. There were two drivers, the Apollo moon mission and the Minuteman missile. And they needed very small, light, highly reliable components. That's what drove the integrated circuit. Minuteman would pay $1,000 for an integrated circuit. And it was during that period of time that the industry found its feet, was able to truly be able to drive the cost down on integrated circuits to the point where they became compelling. You had to have it. Don't ever underestimate Sputnik and the Cold War as being drivers in this period of electronics and computers and all the things that we have today. Now, I have a summary. This is my last slide. What are Kilby's accomplishments? Well, he did his work before Noyce. He was the first person to actually demonstrate by building integration. His structures were the flying wires, were in essence hybrid integrated circuits. But Kilby did demonstrate the IC structure, although he never really built the monolithic. He had implied in the text that it might be done. The thing that he lost on is when they said gold. There was a professor from Stanford that testified at the court hearing that basically said gold does not adhere well to silicon dioxide, and therefore you have to rule it out. I know who that is. I will never name him. I don't know whether you read the other source that will name that person. But little things make a difference in defending patents. Finally, Noyce, he used Hernay's planar process and also Lithography's junction isolation. He did propose the true monolithic version of the IC, which is what's used today. So I would argue that there are others that might have been included in the heading of the inventors of the integrated circuit. I hope you agree. And with that, we have used up 60 minutes, and I will take questions.
Yeah, when Kirby invented these flying wires, now if these wires were just going over each other, there would be a chance that they would connect to each other.
Yes.
Were these wires now somehow maybe isolated? Or
No, that was a problem.
Yeah.
They were bare wires. Just as they are in a lot of hybrid integrated circuits today.
Because even with basically movement of these,
Yeah.
we just said.
Well, that was a reliability issue, and that's one of the reasons why. That's just another reason the monolithic IC were won out, basically.
Right.
And also, ultimately, why did the monolithic version win out? Cost. Think of it when you think of hundreds of millions of transistors on a microprocessor chip today, or a memory chip, and you got to interconnect all of them. It all comes down to how cheaply can you do it. Yeah.
Why didn't they use copper early on as an interconnect material?
Well, today, of course, people do use copper.
Yeah.
Copper is, if copper, for whatever reason, with a contaminant or higher temperature, gets loose, it's anathema to silicon. You have to encase the copper so that it's isolated. Now, the dual damascene processes that are used today with 8-layer, 9-layer metal processes, Intel, IBM, they use copper metallization now because it's lower resistance than aluminum. But in those days, in the early days, they didn't have the technology yet, and aluminum worked well. Mm-hmm. If it works, don't change it. Other questions? Okay, well anyway, I hope that gives you a little bit of flavor of the invention of the integrated circuit. There, you have to give Noyce and Kilby and Hernay a lot of credit, because very seldom does someone get to invent something that has such an incredible impact in the world. And the only person, incidentally, that never got rich was Shockley.
Yeah, by the way, there are a couple of people in Bell Laboratories who were not easy to work with. One was Shockley, the other one was Cyan.
Yeah.
And you know that, Bell Lab basically did the Unix, they did the C programming, they did the C++, they did the Shannon's theorem, and then also a bunch of other ones in addition to the transistors, which are really so important. And these were all done to make the switches, electronic switches, so that we can make communication. By the way, we did also the fiber. I mean, in 1972, they came up with fiber optics to allow very low loss, very low dB, just to go 1 kilometer, just 1 kilometer of fiber. I mean, it was very important function. So I would like to thank Don, who really did an excellent job in presenting all of these things. A lot of us, do not appreciate maybe how important these things were, so that now we can have in our laptop basically a chip which has about 380 million. Am I complete on this one now? Right now there is 382 million transistors. In fact, when I talked to Don a month ago, so he told me the number, so he knows that. So imagine that you have on one chip, and this is just an Intel, it's not a big thing. One chip is about maybe a couple of centimeters of each thing. 380 million transistors. Think about all of these, shall we say, the heat that this thing can make. I mean, we are talking about millions of those. So, thank you very much, Ron.
Let me just leave everyone with one question. You saw all the work at Bell Labs that led up to this. Why didn't Bell Labs invent the integrated circuit? I'm not going to answer that question for you. Something to think about.
Okay. Let's